Pydantic AI routes synchronous tool functions onto background threads so that an agent's event loop remains unblocked. And this thread lifecycle can be governed either by attaching a ThreadPoolExecutor as a ThreadExecutor capability to a single agent, or by scoping it globally through the agents using ThreadExecutor Context Manager. The code below demonstrates both registration paths, each controlling worker count and thread naming to prevent unbounded thread proliferation in long-running servers. A ThreadPoolExecutor with max workers equals 16 is instantiated and either passed as a capability to the agent constructor or yielded inside an async_context_manager decorated lifespan function that wraps the server's active period, after which the executor is shut down cleanly. From concurrent futures, import ThreadPoolExecutor. From contextlib import async_context_manager. From Pydantic AI import agent. From Pydantic AI, capabilities import ThreadExecutor. Hash per agent, pass as a capability. Executor equals ThreadPoolExecutor max workers equals 16. Thread name prefix equals agent worker. Agent equals agent OpenAI. GPT-5. 2. Capabilities equals ThreadExecutor. Hash global, wrap your server lifespan. At async_context_manager. Async def lifespan out. Executor equals ThreadPoolExecutor max workers equals 16. With agent, using ThreadExecutor. Yield. Executor, shutdown wait equals true. This code demonstrates two ways to wire a bounded ThreadPoolExecutor into Pydantic AI for controlling thread lifecycle when sync tools run on threads. The first approach attaches an executor as a per-agent capability via ThreadExecutor, while the second wraps the entire server lifespan with agent using ThreadExecutor as a global context manager. Both prevent ephemeral threads from accumulating under sustained traffic, which is the default behavior with NEO, to thread, run sync. The per-agent path passes the executor through the capabilities list when constructing the agent, giving fine-grained control per instance. The global path uses the async context manager to scope the executor across all agent runs for the lifetime of the server, then shuts it down cleanly. The trade-off is scoping. Per agent lets you tune concurrency per service, while the lifespan approach is simpler when all agents share the same pool and you want explicit lifecycle management in a fast API-style server. Let's break it down line by line. From concurrent futures, import ThreadPoolExecutor. Imports ThreadPoolExecutor for managing parallel execution of callables via thread pools. From contextlib import async_context_manager. Imports async_context_manager from contextlib to enable defining async context managers via a decorator. From Pydantic AI import agent. Imports the agent class from the Pydantic AI package. From Pydantic AI, capabilities import ThreadExecutor. Imports ThreadExecutor from the Pydantic AI capabilities module. Hash per agent, pass as a capability. Executor equals ThreadPoolExecutor max workers equals 16. Thread name prefix equals agent worker. Creates a ThreadPoolExecutor configured for 16 concurrent worker threads, each labeled with the prefix agent worker. Agent equals agent OpenAI. GPT-5. 2. Capabilities equals ThreadExecutor. Creates an agent bound to the GPT-5 2 model with a single capability, a ThreadExecutor wrapping an executor. The agent variable holds this configured agent instance. Hash global, wrap your server lifespan. At async_context_manager. Decorates the following function with async_context_manager to create an async context manager for server lifecycle management, as indicated by the comment. Async def lifespan app declares an async function named lifespan that accepts one parameter called app. Executor equals ThreadPoolExecutor max workers equals 16. Creates a ThreadPoolExecutor with 16 worker threads assigned to the variable executor. With agent, using ThreadExecutor. Enters a context where the given thread executor is active for agent operations. The executor argument is passed to the using ThreadExecutor class method, scoping the executor to the block that follows. Yield pauses the generator function and returns control to the caller, resuming from this point on the next invocation. Executor shutdown wait equals true. Shuts down the executor and blocks until all pending tasks complete. The wait equals true flag ensures the call doesn't return until the shutdown is finished. The two registration paths solve the same problem from different angles. Pydantic AI dispatches sync tools onto background threads via ThreadPoolExecutor to keep the event loop unblocked. And both the per-agent ThreadExecutor capability and the agent using ThreadExecutor context manager gate that behavior through a bounded pool. The per-agent route wires the executor into the agent constructor, giving you concurrency tuning per service instance. The global route wraps the entire server lifespan, yielding control while the executor is active and shutting it down cleanly on exit. The trade-off is scoping, fine-grained per-agent control versus a single shared pool with explicit lifecycle. Both prevent the unbounded thread proliferation that would otherwise come from default NEO-to-thread behavior under sustained traffic.
The concurrency limiter that holds 10 runners lets threads dissolve into the executors, breath, and vanish.